think we can start now. Hello, everyone. Welcome. Thanks for coming. It's my pleasure to introduce Dr. Yashar Akrami. Dr. Akrami is an assistant professor in the Institute for Theoretical Physics, UAM-CSIC in Madrid, Spain. His academic journey is truly inspirational. So he earned his PhD in the Stockholm University, Sweden. And since then, he has held so many research positions in many esteemed institutions, such as Heidelberg University, Leiden University, University of Oslo, and Imperial College. So the list is too long. So without further ado, please join me in welcoming Dr. Akram.
All right. Thank you so much. Thank you, Nilu, for the introduction. I'm really happy to be here today and tell you about some of the things we're doing these days. So, well, I mean, there were different topics I could choose for this talk, but in the end, I decided to talk about the shape of a space, basically cosmic topology. I hope it will be interesting to many of you, I hope. So what I'm going to tell you today is what we mean by the shape of space or cosmic topology, why it is important to actually search for it, and how we are planning on doing it. Okay. So this is part of the work we're doing, as a collaboration. The collaboration is called Compact, as you see here. Collaboration for observations, models, and predictions of anomalies and cosmic topology. We are around 30 people at the moment. We're mainly theoreticians, but well, theoreticians who work with data as well. So yeah, so I guess with that, I'll start. Let's see if that works. Okay, first one. Okay, so I'll start with telling you what cosmic topology is, what we mean by that. So basically, cosmic topology is the study of the overall shape of the universe. Okay, so what we care about is the global features of our three-dimensional space. So that's like the global shape. Okay, and I'll tell you more about that. But of course, there are some local geometrical properties of the universe, such as curvature, that also are very important when you search or talk about cosmic topology, and you will see that as well. So the questions we want to answer are very fundamental. As you can see, some of them here, basically, we want to know, for example, if the space, like the entire universe, finite or infinite. The other question is whether space is simply connected or multiply connected, and that's what I'll tell you what I mean by that. Or, for example, questions like whether space or the entire universe is smaller or larger than the observable part of the universe. Okay, this kind of question. So it's all about the global properties of the universe. So topology itself is a branch in mathematics. And basically, that's the mathematical study of the properties of any objects that are preserved through three things: deformation, twisting, and stretching of the objects. Okay, so you can do any of these things. And if these properties do not change, that means that you are basically talking about topological properties. And one thing that is not allowed is tearing. So you can do anything you want, but you cannot, separate. You cannot break the object into the separate parts. So if you do that, then you change the topological properties. So there is this joke. The joke is, the question is, what is a topologist? And the answer is someone who cannot distinguish between a donut and a coffee cup. So as you see here, this coffee cup has like a handle here. So there's a hole here, and you can use these transformations. You can do the deformation, twisting, and stretching of the coffee cup, and then you can basically create a donut. So one thing that is common or the same in both of these objects is basically this hole, right? So you cannot get rid of this hole. That means that the topological properties are are preserved, but of clearly geometry is different. So that's what you can do, right? You start with the coffee cup, and then eventually you get a donut. So I'm trying to give you some ideas of what I mean by topology. And obviously, these are two-dimensional objects, I mean, two-dimensional surfaces. So, for example, if you look at these objects, a sphere, a torus, or a double torus, or a triple torus, you see these are, I mean, immediately you can say that these are different. And the difference really is about the number of holes you have in these objects, right? So, for example, if you look at these objects now down here, I don't know, like pick, for example, this chair here. You see this chair, again, using those, transformation, I can I can see that this chair has the topology of a double torus because it has two holes in it, right? So I can basically change this one to a double torus, but nothing else. So that's basically the topology of this is a double torus. We can show this. Let me see if I can get rid of this thing here. I'm just seeing myself. Okay. So one way of describing the topology, for example, for a two-dimensional surface, is through these diagrams. For example, look at this diagram, this one, which is a disk. So there is this point A, B, these points A, B, C, and D, and these dashed lines basically mean that this goes all the way to infinity. So you go this way, or that way, or that way, or this way, and you can continue forever. This is like a plane. This is a disk, right? Now imagine for another object, I basically identify this point A and B, these 2 points, and identify these 2 points C and D. So now I have A and B here and A and B here. So this side and this side are basically identified. They're the same. That means that if I go up, I can continue forever. If I go down, I continue forever. But if I go to the left side, I basically come in again from the right, and vice versa. So this is the topology of a cylinder, like a tube, right? You can imagine. I can do something else. I can say, okay, well, I identify these two sides, but also let's say I identify these other two sides as well. So if I go up now, I come again, I enter from below, so that will be like a torus, okay, a two torus. Oh, one other thing I can do, okay, let's look at, for example, this case, a Mobius strip. So on along this side, basically this direction is infinite, but this direction, I identify these two sides, but with a flip. So if I exit from A, I enter basically from B. So it's like a 180 degrees of like, kind of twist. This is a Mobius strip. So and then you can see like a Klein bottle. So all these cases. So let's look at, for example, this example. See, this is a plane. I identify two sides. I get a cylinder, and then I identify the other two sides, and I get a torus, right? So that's how you go from a plane to a torus. So there are different topologies. So the topological properties of these objects are different. Well, that could be a good and okay. So before that, sorry. Spoiler. So the point is that by doing that, I'm not changing the curvature or intrinsic curvature of this object. So all of these three objects have flat curvature. So a plane, of course, is flat, but a cylinder is also flat. By that I mean the angles. Some of the angles for a triangle basically sum up to 180 degrees. So it's flat. So it means that topologically they are different, but geometrically they are all flat. Now that means that I can in principle have a flat Earth, which is finite. Maybe that's good news for flat earthers, but yeah, so basically that is an object that is flat and it has a non-trivial topology. Okay, so these examples I was talking about, like Mobius strip, for example, is this shape. So you have to go twice to get, when you exit once, the handedness changes. So you have to go twice to basically get the same handedness or chirality. So that's the Mobius strip. And this is one of the most complicated cases for a two-dimensional surface, which is a Klein bottle. And you see here that you identified both sides, but with a flip as well. Anyway, so this shows you some topological properties of different objects. Now, there are some properties. So we basically classify topology into two kind of broad classes. One is the so-called simply connected or trivial topologies. So how do we know if an object has a trivial topology? So first of all, it must be path connected, and every path between 2 points can be continuously transformed into any other such path while preserving the two endpoints that you have. So that means if I have 2 points in this space, and if there are two paths here, so I should be able to go from one to another one by just a continuous change, okay? If I manage to do that, that is basically simply connected. Another way of seeing it is like on this sphere, for example. So a sphere is simply connected because every loop on this sphere can be contracted on the surface to a point, right? You can go from this one eventually to a point. If you manage to do that for all the loops in that space, that's also trivial. So these are two equivalent ways of talking about trivial topologies. So that's one thing. But of course, then the question is, what else can we have? Well, we can have multiply connected spaces or surfaces or manifolds, and we also call them non-trivial. And what do we mean by those? Effectively means what we're talking about, the manifold with holes. So if you have a manifold with holes like this one, if I now have this loop, there is no way to actually change this loop to a point continuously, right? Because there is this hole that will not allow me to do that. One example of it is a simple torus, two-dimensional torus. And you see, for example, this loop, you can never get rid of it. And there's also this loop that you cannot change it to a point. So this torus has a non-trivial topology or multiply connected topology, okay? So these are basically two classes of topology. Now, the question, of course, that we are interested in is not about topology of objects, two-dimensional objects, but we are interested in topology of the universe, of the entire space, or three-dimensional space. But what are the possible topologies for a three-dimensional space? So there is this conjecture. Well, it used to be a conjecture, but then it was proven by someone. So it's called Thurston's geometrization conjecture, but then the Russian mathematician Perelman proved that. Now it's a theorem. And what it says is that every compact three manifold, I mean like three-dimensional space, every compact, meaning that all the dimensions are actually compactified, so they're finite, is the connected sum of irreducible pieces, each of which admits one of 8 homogeneous geometries. So these 8 geometries. So 3 of them you all know. One is E3, which is the three-dimensional Euclidean space. The other one is S3, which is this three-dimensional sphere. And then H3, which is a three-dimensional hyperbolic space. Okay, and then there are some other cases. For example, you can have S2 cross E1, like Euclidean one dimension, and then you compactify. You make like a spherical compactification for the other two, and you can do also H2 cross E1, and there are some others that are a bit more complicated. So this is great because if you have a complicated manifold like this, you can break that into different pieces, and each piece admits one of these geometries. Okay? So let's look at some examples. For example, let's focus on E3, which is a simple, flat Euclidean space. Okay, before that, actually, let me show you some examples. So for example, let's focus on these three, E3, S3, and H3. So E3, as I said, is the Euclidean space. It's flat, so curvature is 0. Well, I mean, you can compactify that. So if you look at this what we call fundamental domain, that's the entire universe, the entire space. Then if I identify this basically this side with the other one, that's basically one direction, and then I do the same thing here and also here and here. So that gives me a three-dimensional torus, right? So for example, if the Earth is here, then you can see the images around you. These are basically not real. It's just the fact that if you exit, you enter, and that you can put everything together, and you can tile the entire space like mathematical what we call covering space in this case. You can do the same thing for a spherical or positively curved space. There are also possibilities to compactify these spaces. You can do the same for hyperbolic spaces, negatively curved, and you get different topologies. So one thing that is important is that mathematicians show that if three-dimensional space well, has non-trivial topologies, the number of these non-trivial topologies is known. So we can only have 17 non-trivial topologies for a tree space. So of course, in total, we have 18 topologies, possible topologies, but one of them is trivial. It's just an infinite flat space. But there are 17 non-trivial ones. And each one of them has up to 6 real parameters. And these parameters are like, for example, these length scales, like 3 of them here. Then you have like triangles, because these fundamental domains can be tilted. And so you get basically 3 parameters. For spherical cases, you can show that unfortunately we have infinite number of possible topologies. But the good thing is that it's countable infinity. So we have basically we have a countable infinity or infinite number of topologies, and they have been classified. Okay, so there are a few classes, and then the free parameter for this for each class is basically just the curvature. So these topologies are called rigid. So meaning that just one parameter will basically change that, but you cannot change other things. For the hyperbolic space, if we show that we live in a universe with a negative curvature, then unfortunately we have not been able to classify these topologies yet. By we, I mean like mathematicians, right? So this is very hard. So you have infinite number of possible topologies, and they are not even classified yet. So it's kind of complicated. But in any case, the point is, as I will tell you later, there is no reason for our space to actually be any of these things, a priori. So we need to search for it, because all of them are basically equivalent. So let's look at, for example, the Euclidean ones. These are the 17 non-trivial topologies for a flat space. So we call them E1 through E17. It's just a name. For example, the first one, E1, is a simple tree torus. So if you exit, you enter from this side, and all these directions are basically identified. We have like this E2, which is the same, but then when you exit and then enter, you basically flip like with 180 degrees. So that's called half turn space. Then you can have quarter turn space, E3. You rotate by 90 degrees, and there are some more more complicated topologies as well. So let me not go through all of them. But the point is that we have all of these cases, all these basically 10 that are fully compact. So there are 3 compact dimensions for this E1 through E10. But then we also have 5 others where we compactify only we compactify only 2 dimensions, and these are called chimney spaces, because one direction is actually infinite and the other ones are not. And then we also have the so-called slabs, where we compactify only one dimension. So the rest, the other 2 are actually infinite. So these are the possible topologies for a flat space. Another interesting thing is that some of these are orientable, like these ones that I'm showing here. They're orientable, meaning that when you exit from any of these directions, you basically do not change your handedness. So if you're right-handed, you come in again with right-handed. But there are also other topologies, these ones, that are not orientable, meaning that, like for example, the example of Mobius strip in 2 dimensions, where you have to do this like twice at least to keep your handedness. These are called non-orientable manifolds. The point here, as I mentioned before, is that each of these manifolds have some free parameters, like the length scales, tilts, and also for many of them, it's important where we put the observer. So because they are not homogeneous, so that means that the location of the observer matters. Not for all of them. For example, for Taurus, that's basically homogeneous, but for the rest of them, they are not homogeneous, so the position of the observer matters. So for cosmologists, that's basically some kind of free parameters where we are located in this universe. Okay, so first of all, let me say that the question of what the topology of the universe is an observational question. The reason for that is that general relativity, which is basically the theory of gravity, the standard theory, particularly for gravitation, but very important for cosmology, is a set of local differential equations, which means that it doesn't really care about the boundary conditions, and it cannot really tell us what the topology or boundary conditions are, because topology is nothing but just a boundary condition, okay, of the universe. So by that I mean, if you look at GR, these are the differential equations that you have to solve, but when you solve a set of differential equations, you have to specify the boundary conditions for that system, right? And those are not part of the equations. So they have to come from something else. And GR doesn't tell us what the boundary conditions are, so we need to just go out and measure and observe and see what the boundary conditions are. So searching for topology of the universe is actually an observational question. Okay, so now I told you, what topology is. We are trying to find that for our universe. But then the question is why? Why do we search for cosmic topology? There are different motivations. Some of them are purely theoretical. So for example, the first reason is that, we are cosmologists. So cosmologists study the universe. And when somebody studies something, the first question that you might ask that person is, okay, what is the shape of the thing you are studying? And for cosmologists, because we study the universe, knowing the shape and volume, of the universe, whether it's finite or infinite, or what is the shape of it, is really important. This is an old question for cosmologists, and maybe for humans actually. So maybe 10,000 years ago, people were asking the same question. Oh, is our universe finite or infinite? So that's obvious. Well, that's an obvious question. The other reason for why we are interested in the topology of the universe is that if we measure the topology of the universe, then that would be a truly remarkable physics accomplishment, because we would know the full extent of a space and we would be able to map the entire universe. And that's really exciting. That's like basically mapping the entire Earth, right? So we would know everything in it. Also, if you discover a non-trivial topology for the universe, that would require significant rethinking of the earliest epoch of the universe. What do I mean by that? So first of all, we would know that if there was an inflationary epoch in the early universe, like to set the initial conditions, then it could not have lasted long enough, because if it lasted really for a long time, then the scale of topology would have been so big that we would not be able to see that, right? So the universe would become so big. So if we detect topology, the topology of the universe, that would mean that that inflation had not lasted, for a long time. Also, inflation would not be the explanation for the approximate homogeneity of the universe, because again, inflation, if it lasts for a long time, then all the inhomogeneities will go away. And if we detect the topology, that means that the inflation did not last for a long time. So that means that cannot explain the homogeneity of the universe. Also, discovery of non-trivial topology would have enormous implications for the theory of quantum gravity. There are old papers actually, going back, for example, to Stephen Hawking, like this paper from 1978. There are some ideas like quantum foams and all that, where in the early universe, because everything was basically, everything was quantum, so you have all these quantum fluctuations, and topology can change. It's like a foam, basically. And it's very important to if, for example, detect non-trivial topology for the universe, then you would ask, okay, where does this universe with finite volume, whatever, come from? And that is a question that people who are doing quantum gravity should answer. Another motivation for people who are interested in things like string theory is that maybe actually string theory, if it's the right description of our universe, has already told us that the universe has a non-trivial topology. The reason for that is that normally in string theory, you need many more dimensions than just three, and we need to compactify at least 6 of them because we only see 3 big dimension. So then the question is, if we need to quantify 6 dimensions, why not compactify 3 more? So it's natural to also compactify the dimensions that we are seeing. Okay, so I'm not going to go through the rest of them, but there are some other developments in string theory, for example, that suggest non-trivial topology. If you're interested in this kind of proposals, you can check this paper. And also, the other thing is that topology may be the only way to distinguish between 2 interpretations of general relativity. One is this geometrical picture, which is the standard one with curvature and everything. And the other one is this modern view, mainly, well, modern, I mean like particle physics view, in which general relativity is the unique theory of massless spin 2 particles. So when you talk about shape of space, you probably would want to go for this one, the geometrical picture. But if we, so maybe if we detect the topology of the universe, then that kind of tells us that the other view might not be correct. I don't know, but that's more like a speculation, but it's very interesting. So there are a lot of theoretical reasons for why we think detecting an non-trivial topology for the universe is very interesting. So let me just read this statement here. A finite universe carries with it a host of philosophical, observational, and theoretical consequences, no less monumental than the discovery that the Earth is round. Having found cosmic topology, we might be in a position to know all of the universe, not just a small corner in which serendipity has placed us. Okay, so it's really interesting to know the shape of the universe. All right. But in addition to all these theoretical motivations, there are some observational hints or implications that are also very important. So one of them is that maybe we have already seen the effect of cosmic topology. Maybe we have already observed that. The reason for that is that there are some weird things going on very large scales on the cosmic microwave background sky, what we call large scale anomalies. And these anomalies well, we don't really have any good explanation for these anomalies at the moment. And as I will argue later, topology might actually explain that. Okay, so this is something that kind of motivates us from the observational point of view. In addition to that, if we detect cosmic topology, that would complicate current plans to search for various other signals beyond the standard lambda CDM model. For example, if you're searching for dark energy, modified gravity, or primordial non-Gaussianity, the reason for that is that non-trivial topology violates statistical isotropy and possibly homogeneity. And that means that when you're searching for something else, you cannot assume that the universe is isotropic, and things will become more complicated. Okay, there is a third one in connection to cosmological tensions, but I'm going to skip that for now, but we can discuss that later if you want. All right, so let's look at the anomalies a little bit, because I think that's very important here. So if you look at the cosmic microwave background, I mean, this goes back to COBE, 1992. We had COBE, and then we had WMAP with much better precision, and then Planck after 2013. So that's the cosmic microwave background sky. And people who have worked with the CMB, they know probably from kindergarten that the way we describe these fluctuations is by expanding them or writing them in terms of this spherical harmonics, and these coefficients ALMs are basically like Fourier modes, for example, for a three-dimensional space. These are on a sphere, and that's how we describe these fluctuations through these spherical harmonic coefficients here. So the standard model for the fluctuations, something like inflation, tells us that the sky is statistically isotropic. Okay, so all the properties on all directions are basically the same, statistical properties. Also, it tells us that these ALMs, these coefficients here, are independent Gaussian random variables. This is the assumption. This is coming from the standard model. Now, then we write down the two-point correlation matrix, basically, for these ALMs. And then we can show that under these assumptions, you can simplify that a lot. So under these assumptions, this covariance matrix becomes just some number, some quantity which has index L, and then the Kronecker deltas here. So it's just diagonal. So this matrix becomes diagonal in that case. And these C's of L's here are the angular power spectrum, basically. So, okay, well, that's what we do in standard cosmology. And then we can go and measure this CL. And we know that there are some estimators for this quantity. And we can show that all the interesting information is contained in this estimator that is defined this way. But of course, in general, when you don't have a statistical isotropy, then you cannot work with this power spectrum. You have to work with the full covariance matrix, something that has four indices, L, M, L prime, prime. Okay, so that's when you break statistical isotropy. So, of course, people wanted to measure, to check whether the universe is actually statistically isotropic or not. So this was done by many groups, including the WMAP and Planck collaborations. And there are some, for example, 3 papers by Planck that did that exactly, like different ways. And I was on 2 of these papers. So people checked this, and they found out that there are some large-scale anomalous features on the CMB sky, the temperature sky, that are unexpected or extremely unlikely to happen in lambda CDM, the standard model of cosmology. The list is very long. I'm not going to go through these things. So there are different types, like so-called lack of large angle CMB temperature correlations, or hemispherical power asymmetry, quadrupole and octupole alignments, point parity anomaly, cold spot, and many, many, many others. So the point is, if you compute the p-values, which is the probability of our universe to be consistent with an isotropic universe, given any of these anomalies, you get something like less than 0.1% chance of that to happen within lambda CDM. Okay, so it's significant, but not very significant. It's like, that's why it's called anomaly. It's not a detection, but it's very curious why they're not happening very, why are not happening all the time in lambda CDM. So, and the point is that almost all of them, maybe an exception of the cold spot, imply violation of a statistical isotropy. Okay? So there are some papers you can check. There are some review papers, and we are preparing another one, a big one, maybe 200-300 pages. It's an invited review paper. So stay tuned for that. So there are all these features that are really curious. Recently, with Glenn Starkman and other collaborators, we wrote a paper with this title that the universe is not a statistically isotropic. And in here, we basically showed that if you look at the probability of these anomalies to happen on the tail of the distribution, not all of them, just a few of them, we just chose randomly some of these anomalies. We did not tune them. We did not do any cherry picking or anything. If you look at the joint probability on the tail, you see that you basically get more than 5 sigma significance for a universe that is not statistically isotropic. So we are claiming that the sky appears not to be a typical realization of a Gaussian random statistically isotropic field. Okay, this is a big claim, but we think it's correct. So with that, let me see. Yeah. So right. So there are. I think actually, let me see. Do I? Okay. Yeah. So there are ways to explain these anomalies. So we can come up with some fundamental physics models to explain the CMB anomalies. There are two requirements for such a model or such a theory to do that. First of all, it should break a statistical isotropy, as I was saying. So they should generate off-diagonal elements in the harmonic space two-point correlation. So this CLM L prime prime should actually not be diagonalized, the diagonal. And that's required because all these anomalies are basically violating statistical isotropy. In addition to that, whatever this mechanism is, it must affect scales that were causally disconnected until recently. By until recently, I mean like until the CMB entered the horizon. So this is quite hard to satisfy using microphysics because there are kind of scales that are that were outside the horizon and they were still correlated. So microphysics cannot really do that as far as we can say. So our best bet is to change the boundary conditions of this universe. And by that, well, that's the same as changing the topology or basically by having a non-trivial topology for the universe. So we think topology can actually potentially explain these anomalies. So for example, if you look at the list of these 18 different topologies for a flat space, you see like the ones that are in yellow, they are orientable, and the other ones are not orientable. But all of them, except for this E18, which is the trivial space, what we call covering space, all of them violate the statistical isotropy. And that's obvious because you have preferred directions. The space has shapes, orientation, and all that. So they all break isotropy, not through the metric, but through the boundary conditions. And some of them also break homogeneity. So it is possible to get that. And you can see an example, which is this simple, basically E2, which is a torus with a flip on one side. So now you see if you compute the covariance matrix, this so-called this CLM L prime prime, or normalized to some number, doesn't matter. So you see it's not diagonalized. It has all the off-diagonal terms, and there is a particular pattern. So, but if you are able to measure this covariance matrix observationally, that should give us hints of what the topology of the universe is, and whether this can actually explain the cosmic anomalies. So we formed a collaboration. It's called Compact, as I was saying in the beginning. These are some of the members at the moment. So this is a 10-year program. We want to use all the cosmological data. By that, I mean the CMB, largest scale structure, 21 centimeter data, to understand cosmic anomalies and to discover the topology of the universe. Well, to discover only if it's possible to discover it, or we want to demonstrate conclusively that discovering the topology of the universe is beyond our reach for the foreseeable future, or maybe for the next 50 years or something. So this is a highly ambitious plan, but we are trying to measure the topology of the universe. Okay, and there is this paper, it's a PRL paper that we put out like two years ago. This is where you can see if you're interested in our in knowing our goals and motivations and search strategies and all that, you can check this paper. And here we describe our plans for the next, I don't know, 10 years or so. Okay. Okay. Now the question is how to detect cosmic topology. So let's see. Okay. So the first idea that people actually proposed was through the so-called topological clones. Okay. So in here, the idea was to search for pairs of identical astronomical objects on the sky. Why that is something that could actually tell us about topology. Imagine we are living on this two-dimensional universe, a torus, two-dimensional torus. If you're sitting here, then light will go like this. Like if you emit a light, some kind of light, ray, it will go like this and it go back, go like along this loop, and then we can see that again. So we can see ourselves, right, after some time. It takes some time, but we can see an image of ourselves. And if it does it this way, the same thing happens, okay? So I can show that on this plane. Imagine this is the universe, and we are sitting here, and this is some kind of star or galaxy or something. And then light goes to us, of course, directly. But because this side and this side, basically these are identified and the same here and here. So the light can actually go out and come back to us. And that is why, then that means that we can see the same object, for example, coming from here, the light coming from here. So we can see all these clones of all these objects. So if you look at the sky, you might be able to see, oh, look, I mean, there is a star here, but there is the same star somewhere else, or same galaxy or whatever. So so if you see these identical objects, then that is a sign for cosmic topology. Okay. There is an issue though here. So the main issue is that these clones would be seen at different ages, from different perspectives, and along different lines of sight, right? So it would be really hard to know if this galaxy and this galaxy are actually exactly the same, because first of all, the orientations are different. They're coming from different times. So we might not know if it's actually exactly the same object, right? It's younger or older or whatever. So this is a really the main problem. So how would you know that these are the same objects? So this was the first idea. People worked on that, but then some people in mid-90s, like 1996 to 1998, Cornish, Sperger, and Starkman, they came up with a very nice idea. So they said, okay, well, instead of looking at like objects, let's look at the cosmic microwave background sky. So the good thing is that, basically, all the features on the sky, on the CMB sky, they're all coming from the same time, right? Approximately from the same distance from the observer. And that means that all from the same cosmic epoch. So let's look at an example. Imagine the universe is two-dimensional. I'm identifying these two directions, this direction, well, these two kind of sides, but it's infinite from the top and the bottom. So, okay, so it's just one compactified or compact dimension. Now, I can tile the covering space with this. So if I go this way, I come back like here. So that means that effectively I have these clones, right, on this direction. Now, if I'm sitting here and this is the CMB sky I'm seeing, if the CMB sky, the last scattering surface, is larger than this distance, then what happens is that when I'm looking at this point is the same as this point, right? And this point is the same as this point. So I can see it this way, that these are my clones, right? And each one of them is seeing a CMB sky around it. But then these 2 points are identical. So if I look at like the CMB sky, I should see the exact same value here than here, right? This is a two-dimensional case. But for a three-dimensional case, which is our universe, what happens is that I should see identical circles, on different parts of the sky, but they should be exactly identical. So whatever is exactly on this circle, for example, should be on this circle. So this was a very nice idea. So people searched for these circles to see if actually there are any circles, and they couldn't find any circles. There are some papers that you can see here, also including the Planck papers on topology. So people could not find the circles. So that is why the conclusion was that the distance between us and our nearest clone, which is the shortest loop in the universe through us, is actually larger than 98.5% of the diameter of the last scattering surface, or the CMB. Why not 100%? Because at some point, these circles become so small that we don't have the resolution to know if they exist or not. Okay, so we cannot really go to 100%, but almost 100%. So that is telling us that the CMB sphere is smaller than the compactified dimension. Okay, to some extent. So when this happened, people stopped working on topology, many people. So this was widely misunderstood to mean that the shortest distance across the universe is greater than this, diameter of the last scattering surface. Even though we had only done it, we had only measured for this loop or this, shortest distance through us, not anywhere else in the universe, right? So that means that there is a lot left to actually search for, even by that. And in this paper, we went through some of the cases, orientable Euclidean manifolds, and I'm not going to go through the details of that, but we showed that a big part of the possible topologies, even small topologies, okay, are still not ruled out. So there could be some circles on some other basically CMB skies, but we don't see them. But the dimensions can actually be quite small. So sometimes even by a factor of like ranging from 2 to at least 6, smaller than the diameter of the last scattering surface, but those universes are still allowed observationally. So this was the paper that we wrote 2 years ago, 3 years ago, and we are now doing the same thing for the non-orientable Euclidean manifolds to translate that length, 98.5%, into the parameter space of these models. We have also, okay, so here it says in preparation, but this one is out. This paper is out. We have done that also for the spherical S3, some of the topologies, and we have put some limits just from not seeing the circles. But we have shown that there is a lot left to search for. All right, so now that we know that the universe is not very small, possibly, how can we actually measure topology if the CMB sky is actually much smaller or smaller than the topology scale? Imagine this is our universe, and this is the CMB sphere, and this is smaller than this length scale. That means that there is no circle, there are no identical circles on the CMB, but then can we still measure the topology? The answer is yes. So when you have an non-trivial topology, that changes the spectrum of the acoustic modes for any observable fluctuations in this universe. So if you have, for example, a Fourier mode like this or this or this, the point is because of boundary conditions, okay, so this would mean that some of these modes are not allowed because you have to satisfy the boundary conditions. So this is like what boundary conditions do to sound waves, for example. And sound waves here are everything in the universe. CMB, large scale structure, 21 centimeter, everything. So there are things that happen to these modes. Topology does two things to all these modes. First of all, it discretizes the modes because not all the modes are allowed in a box. The second of all, many of these topologies actually correlate these modes in a perfect way. Because if you look at think about that in Fourier space, like modes K1, K2, K3, so they have to somehow relate to each other such a way that that the whole combination is allowed. So there will be some perfect correlations between different modes. So this is like the mathematical question, an old question. Can one hear the shape of a drum, right? If you listen to the drum, can you actually guess the shape of that? This was a problem this mathematician worked on in 1966. And now the question becomes for us, can one hear or infer the shape of a three-dimensional cavity with imperfect ears because we don't have perfect ears? So that's the way to move forward. So in this case, we don't care about the circles. We really try to measure these correlations and these spectrum and so on. This is a spectra for different observables, and that will give us information about topology. So let's look at some examples. So as I said, we have discretization and correlation that these things encode breaking of isotropy and homogeneity by the topological boundary conditions. So they would generate non-zero off-diagonal elements in this correlation matrix. Okay, because I have to be a bit faster. So an example, for example, is again this E2 topology. So first of all the modes you can show that are now discretized. And also if you look at the covariance matrices, like in Fourier space, you see that it has more complicated form. So there are some terms that are not standard. The first piece is the standard for the covering space, but then you get some other eigenmodes and all that. So the covariance matrix is more non-trivial, complicated. And then for the CMB, which is this quantity, CLM L prime prime in harmonic space, that also has this complicated form with these functions that are topological, these terms. And these are also have some non-trivial forms. So Well, again, as a summary, you can see that this covariance matrix would now have all these off-diagonal terms in it, right? So this is an example of how topology can break a statistical isotropy. So you can look at this paper of ours for Euclidean orientable manifolds, and you can see a lot of examples. We basically calculated all these covariance matrices for all of these topologies. Okay. So the Planck collaboration studies some of these topologies, but just a very few of them. So I'm not going to go through that, but what I'm concluding from this is that what Planck told us, they use some of these techniques, but it's basically measure zero in the space of possible topologies, what they did. Just very simple topologies, like effectively just E1, three torus, and also for that, even cubic one. So all the Lexis scales are the same. So there is a lot left to do to basically search for topology. Let me give you an example of what we are doing now. So I don't know, maybe you're familiar with this. There is this quantity that is called KL divergence. KL divergence is a Bayesian quantity. The simple question that you ask when you're computing this is this. So you have a model, you have two models, and you have one data set. You want to know how well this data set can actually distinguish between these two models, okay? So if you compute this, which is an integral effectively over the probabilities of this data coming from two different models, in this case, trivial topology and non-trivial topology, you compute this quantity. If this quantity is larger than one, or roughly, it means that you can distinguish between, for example, trivial topology and non-trivial topology using the data set. In this case, it's a CMB. If it's smaller than one, you cannot. So this example is showing, well, it's just one example. So look at E1 and E2, two topologies. What is this figure? So we are fixing two of the Lexis scales to something like 1.4 times the diameter of the elastic scattering surface. So there are no circles there. They're large, right? They're big. And now you change the other dimension, the size of that. And when we are below one, it means that the universe is small. So there are all these intersecting, CMB spheres. So it means that there are pairs of identical circles. And in that case, you see the K divergence is quite large because there are circles. But then you're interested in cases where there are no circles on the sky, which means that this quantity is larger than one. You see the K divergence actually goes down, and it eventually is below one, but not immediately. So if the universe is, I don't know, 20% larger than the size of the CMB, you can still detect it, okay? So there are many examples like that. So you might say, okay, this is great, but what if the universe is actually much larger? So it means that the CMB cannot actually tell me that, right? It can detect the universe only up to, I don't know, 20% larger than the elastic scattering surface. Yes, that's right, but there are ways out. Um, First of all, this is with the CMB. CMB is a sphere, and there are some projection effects and dimensional reductions on the CMB, and you basically mix infinite number of many modes, Fourier modes, that coming from topology, and that is why if you go to smaller scales, you cannot really improve this one. So the one way forward would be to use three-dimensional data, or what we call four-dimensional, because one dimension is time. Like, for example, from the largest scale structure or 21 centimeter data, you probe the interior of the universe, and that should actually give us a lot more information. So we should be able to move this to the right, significantly. But there is another reason for this. So the thing is, if topology, this is a big if, but if topology is the physical cause of CMB anomalies, that means that there must be, that CMB must contain some detectable topological information. So this figure shows us if the universe is very big, then there is no information on the CMB to detect this topology. But if anomalies are coming from topology, that means that there is information. So it means that most probably the universe is not very big. So maybe 10, 20% larger than the CMB. That means that if you push a little bit by adding other data sets and so on, we should be able to detect the topology. Okay, so this is one of our motivations for searching for the topology, because we basically think the universe is not very big. And well, But again, this is only if we show that cosmic anomalies can be explained by cosmic topology. All right. So I need to be a bit faster. I know it's like 1 hour now. So first of all, there are different questions we want to answer. For example, we want to classify topology or topological models using the data sets. We want to know, which topology is more likely for the universe. We want to also estimate the parameters of different topologies using the data. We also want to know if topology can address cosmic anomalies and tensions potentially. So, and also we want to know the impact of cosmic topology on cosmological parameter estimations. These are questions that we want to answer. And for that, we are building a pipeline or infrastructure to do that. And first of all, we want to combine all possible data sets, like from the CMB to large structure, to do that. We need to do a lot of theoretical calculations of topological effects on physical observables in different regimes, linear, mildly nonlinear, strongly nonlinear regimes, and so on. We need to compute all these observables and covariance matrices. There are different techniques that we are developing. Also, we need to model our data better. And also, we need to use a lot of advanced statistical inference techniques like Bayesian and frequencies frameworks. And so we are basically developing all of these things. All right, so let me give you some other examples. So topology can also do something really interesting. For example, if you look at the polarization of the CMB, for those of you who are aware of these things, many of these correlations between, for example, T and B, we know that in a standard model, they are zero. There is no correlation. But topology, because of the changing the boundary conditions, can actually produce all these correlations. So these are really interesting. This is an example of that. And you can see that topology can actually affect the polarization of the CMB, really in a way that is not possible with lambda CDM. I have another example here when you're also kind of doing something that looks like violation of parity, but it's not really parity that is being violated. It's just because of, again, breaking statistical isotropy. But you can do lots of interesting things that you can go and measure. This is an example of all the possible correlations between temperature and polarization of the CMB for an example, and you see all these patterns that you can go and measure. And this is an example from this Hofstadter space, but of course for each of topologies you can do that. And that is why this is of extreme interest to the future polarization experiments like LightBird. Because topology-induced off-diagonal correlations between T and B may increase sensitivity to tensor modes. That is really useful for measuring the tensor to scalar ratio from inflation. Also, LightBird's measurements are of extreme interest to us, compact, because, well, of course, we can hope for detecting the topology. And that is why LightBird and us, Compact, now we are signing a memorandum of understanding, and we want to work together to basically look for topology in the future CMB data. Okay, so in the future, we're going to have a lot more experiments. These are the CMB ones. And also, we're going to have a lot of experiments that will measure the largest scale structure of the universe. And this will allow us to probe in detail much of the spherical volume of the observable universe. We want to put all these things together to be able to hopefully measure the topology of the universe. I'm involved in some of these experiments. I'm involved in, well, LightBird, also Euclid and SKO and so on. So we're working on these things. Just to show you an example, for example, for the three-dimensional data, we are doing some simulations for different topologies, and we are computing at the moment the scale divergences to see how much information is in there. And then, of course, then we have to make it more realistic and compute the correlation matrices, and then eventually use the data to study these effects. One thing that is important to keep in mind is that if you look at different scales, this is the power spectrum of matter. This is the scale K. This way means like smaller scales, and this is larger scales. So the traditional way of measuring, working with this data is to work with this power spectrum, right? Like P of K. However, with topology, Now we know that we cannot work with power spectra, like for example, the CMB, we cannot only work with Cs of Ls, we have to work with the full covariance matrices. So we have to compute them and then use them in our data analysis. The same thing for the matter for matter fluctuations, basically for large structure, we can no longer work with power spectrum, bispectrum, trispectrum, these kind of quantities, because these are average quantities. They are assuming a statistical isotropy, and you're breaking that. So we need to work with the full covariance matrices, and this is tough. Okay, so basically we have to rebuild everything that we know in cosmology from almost from scratch, with no assumption of a statistical isotropy and homogeneity. So that's really hard, but we are working on that. Also, we need to okay. So as I said here, whatever we are doing, we cannot assume a statistical isotropy and homogeneity in any part of the infrastructure that we are developing. So we cannot work with average quantities. So that's important. The other thing is that we might need to actually use some advanced inference techniques like the so-called likelihood-free inference or simulation-based inference, because these are seems to be the best strategy for the reason is that computing the likelihood for non-trivial topology might not be possible because we have the full covariance matrices. We cannot put them in the code. They are very slow and so on. So there are techniques like so-called likelihood-free inference techniques that some of you might be aware of, and we are trying to develop different kind of strategies. I'm not going to go through the details of this, in combination with machine learning techniques and all these advanced statistical techniques, to step by step build this infrastructure or pipeline to search for topology. Okay, so we have started. There are some first steps. For example, we have developed these machine learning techniques to classify different topologies. They have been working quite well. There are some problems with rotations and so on that we are trying to. I'm not going to go through these things, but there are still problems. Okay, what I'm showing here is a so-called confusion matrices. So there are three examples here, three cases. One is like the covering space, the infinite universe. The other one is the universe that is like half of the size of the last scattering surface, then a smaller one, the smaller one. And our machines have been able to distinguish between them. We basically make hundreds of thousands of simulations. We train our machine, and we then ask which topology is actually for a given data set. And yeah, we are progressing in that direction, and hopefully this will be then combined with the inference techniques. We have been using different methods for this, so this is ongoing as well. All right, so let me summarize. So we must discover the topology of the universe or its shape, or show that it is beyond all possible data to do so. The CMB data taught us that the length of any closed path through our location must exceed 98.5% of the diameter of the observed universe. This is what we know at the moment, nothing more than that. But we should and we can search beyond that. This search has compelling motives beyond our curiosity. First of all, the discovery of non-trivial cosmic topology would have enormous implications for fundamental physics and early universe cosmology. It may also perhaps uniquely explain the CMB anomalies. Non-trivial topology would change the acoustic modes of the cosmic plasma responsible for the CMB and galaxies, basically the entire structures, all the structures in the universe. And the anticipated data from the upcoming large-scale structure surveys, for example, Euclid, the SKO, and CMB observations, for example, Lightbird, will probe in detail much of the spherical volume of the observable universe back in time to its first millennia. So this should vastly improve our ability to identify and characterize the acoustic modes and therefore detect the topology of the universe. So, well, that's a hope, but we don't know. We may just merely extend the current limits incrementally, but also there's a chance that we may be able to map the entire cosmos, and that's our hope. I'll stop there. Thank you.
Thank you. I think we have a question from Garrett. Go ahead, Garrett.
Yeah, I have a couple questions. So first, you mentioned polarization. So like EE polarization, and I think the L's you were looking at were fairly low. how much
Right.
would something like randomization contaminate any sort of statistics you try to run on the polarization signal?
This is a very good question. The point is that we don't know yet. So that's why, well, at the moment, that's why we actually started to talk to Lightbird people. Okay, so we need to really understand all these effects. At the moment, everything I told you is based on a full sky map. There is no noise, no foreground, no mask, nothing. Okay, so we are far from there. But we need to really model all of these things and understand how much that they will affect the detection, possible or potential detection. So I don't know yet. But hopefully, I mean, in a year or two, we'll have some good ideas about that. But at the moment, we don't know.
Okay. And I have another question if we have time. So you mentioned all these CMB anomalies. You kind of argue
Right.
for, you usually argue for like non-statistical isotropy, right? And then you kind of talk about topology. Is there a clear way to explain these seeming anomalies with topology? So, like, for example, are there sets of topologies that would explain why the quadrupole and octupole moments are aligned? Like, is that pathway clear, or is it we'll get there eventually kind of thing right now?
Right. So no, I mean, so that's what you're doing at the moment. Okay. So what you're doing now, we are making a lot of realizations from different topologies, using different topologies, and then we compute the p-values for different anomalies for each topology. So so we have seen some effects, but this is still ongoing. Okay. So there are some papers out there in which they claim, for example, if you have a slab, this slab might actually explain, for example, S1 half, which is one of the anomalies, or it can explain maybe the alignment. But the problem with those cases is that they are basically topologies that are ruled out. For example, the slab, the size is like, I don't know, 70% of the last scattered surface. So we should have seen the circles. We don't see the circles. So this has not really been done exhaustively. So this is part of the plan. We are now looking to different anomalies and different topologies. I can't say for sure topology is going to will explain the cosmic anomalies. We don't know that yet, but because we have a lot of possibilities here. Okay, so topology can actually do lots of interesting things, and at the moment it's more like a hope. Okay, but we don't know if that will be the case. Again, that's another thing that we are working on. So we don't know for sure.
Okay, thank you.
Well, I have a lot of questions, so please stop me if I'm too annoying. But you've already mentioned that topology can do a lot of things. I would ask a simple thing. No, probably not simple, but I think the first thing I should ask. Are you not afraid to break early universe? Because usually whatever I do with the early universe, it's extremely sensitive to everything. And I change something and I break nucleosynthesis in one moment. I break second phase transition and something like this. And I have absolutely zero nothing in my universe, especially if I'm small. So I don't know, probably I don't have any physics intuition for this, but I expect the effects to be more significant when I'm small. Probably it's not true. I don't know.
Right. So, well, we don't think there will be a big effect on those things. So, first of all, those are coming from microphysics. We are not changing those. Okay. So, what you really are doing is, as I said, like discretizing your spectrum, or just basically adding some correlations. And these are scales that, well, in principle, that affects all the scales. But if you go back to early universe, you can see that depending on the size. So if the size of the this universe, the topology scale is not very small, then we do not expect any effect like that. Okay, so these are really boundary condition effects, and we do not expect that to affect, for example, what we get from inflation. Having said that, so that we are working on, basically, we are trying to understand how exactly things like inflation or other physical mechanisms work in a universe that is compact. Okay, so we are studying those, but so far we haven't seen a big effect. One thing that can be different is like the power spectrum, the primordial power spectrum for the fluctuations, particularly on very large scales. But exactly how that will be affected by topology, we don't know yet. Let me just say one thing though. I mean, there is a paper by Andre Linde in 2004, like 20, almost more than 20 years ago. He argues even for inflation, for example, it's actually really good to have a compact universe. This paper you can find, he argues a universe that is flat or hyperbolic and compact is actually good for inflation because inflation can actually work more effective, more efficiently, basically. And but again, what exactly the effects would be, we are computing those, but we don't really think things like Big Bang. These kind of things will be affected by this by topology.
Okay, my other question is about you mentioned multiple times statistical anisotropy, and when statistical anisotropy becomes like what I usually generally call anisotropy, and is it related to this KL divergence you defined later on in slides? Yeah, that's the beginning of the question.
Well, I mean, we know the universe is actually very close to being statistically isotropic, okay? Well, that's why we haven't really detected a big signal. So the signal is definitely small. But what we are claiming based on these cosmic anomalies is that even though the signal is very small, but it's detectable, and we have already detected that, okay? So we are not very far from like a universe that, an isotropic universe. So the signal is small, but we look for it. So in the future, with more data, hopefully, we'll be able to enhance the signal. So yeah, for some, depends on what you want to do. But in principle, for some applications, maybe, I mean, assuming the universe is statistical isotropic is actually a good assumption. But if you really care about, what the actual universe is, like the fundamental properties, then it matters. Even the small, even very low level of isotropic breaking. Okay, so yeah, so this question is like depends on what you mean, or what you're looking for. But it's important to, yeah, sorry.
I asked because I think that if I'm anisotropic, I explicitly violate angular momentum declaration, and I want to know if I will be able to see it, especially probably, I don't know, in the earlier galaxies. So there's probably not a dark flow, but probably this was a recent paper that, probably galaxies rotate in one direction more than another direction. Should be something like this, probably. Do we expect such effects?
Well, so this all depends on, so for example, I mean, at the moment, what we think is that the level of statistical isotropy violation that comes from topology is very small. So it's detectable most probably. That's what we're computing at the moment by adding a lot of modes. If you're measuring, like, I don't know, Fourier modes, like using 21 centimeter, data and so on. So you can detect probably this, but these are not going to be too big to affect, most probably, to affect things like galaxies or orientation of galaxies and things like that. So, but again, the exact answer to this question, we don't know yet. We're computing now the KL divergence and these kind of quantities for different data sets. Well, stay tuned. Hopefully we have an answer to this question soon.
Okay, I have a last tiny one and I promise to disappear. You said multiple times, and I totally agree. I love the theoretical stuff. I agree with that, but you say, okay, we want to know what is the topology of the universe. But I'm better topology. But at the very beginning, you said, okay, there are classes and classes and uncountable infinities of possible topologies. Does it mean that even if I find those as non-diagonal parameters and I know that it's not trivial, I will still have a huge degeneracy in determining what the form, the shape of universe actually is?
It could be, yeah. Depends on how constraining the data will be, how powerful the data will be in terms of distinguishing between different topologies, right? So it seems like if the size of the universe is very big, then there is no hope. If the size of topology is very big, so it really depends on the size, right? So if you're just slightly larger than the size of the observable universe, then the K divergence is quite large between different topologies. That means that we should be able to distinguish between them. Okay, but if the size is, I don't know, like 2 times the diameter of the last scattering surface, then most probably we cannot distinguish between between two different topologies. Okay, so it really depends on what is out there, right? So we are now computing and quantifying these things, but this all depends on what we measure, what will be the result of the measurements, right?
Probably. Okay, thank you very much, and thank you for this very interesting talk.
No worries. Thank you.
Yeah. Are there any other questions? Thank you, Yashar, for joining us today. Hope you have a nice day. Thank you.
Thank you very much. All right. Bye, everyone.
Bye.